Okay, hi everyone. So I actually pushed some data to the repository in order to do some data analysis today. So it's really a tiny text file. You may want to either clone this repository. You know how to clone, right? You should be experts in GitHub and Git now, right? So you can either say git clone, or if you really want to be super lazy, you can maybe just download this populations text file, which is in lectures, data, and populations. I mean, we are gonna use this later in the class today, but in order to make the class continuous, I think you can do it right now. Okay. So everybody has it now? You need some time. Okay. It is in lectures and data. But really, you should just be able to say git clone of this repository. Or if you already cloned it, you can just say git pull origin master. That should work too. Okay? Okay, all right. So let's get started. So last week we talked about linked lists and also classes, right? And your assignment was also about a linked list. So today we are gonna continue with trees. So like linked lists, trees are also made up nodes, and a common kind of tree is a binary tree. Of course, doesn't have to be binary. It can have as many branches as you want, but binary tree is the most common version in computer engineering or computer science. So here each node actually contains a reference to other two nodes. So maybe I should make this smaller for now. So let's say this is our tree, and each box represents a node, and for each node we have this data, and also it has two pointers like left and right, and those two pointers also point to a different node. So this is so much like next in linked list, but here we have left and right instead of just next. So here the top of the tree is actually so it's called root, and the other nodes are called branches, and the nodes with the tips, so these ones with the null references, are called leaves. And also you can also assume that the top node is sometimes called parent, and the nodes it refers to called are children. So that's another definition of this. And the nodes with the same parent are called siblings. So these two nodes are siblings for this tree now. And also, we also have this notion of level. So for example, here, so this is level 1, this is level 2. If you have more, so each of them actually defines the level of the tree. So that is the distance from the root to the node itself. Okay, so this was an introduction for the trees and also some notation or jargon about the trees. So now let's start typing some code. If you have your notebook ready or your PyCharm ready, you can start typing with me now. So here it asks for to create a class called tree, and that takes data and left and right as arguments and creates attributes for those. So let's do it all together. Class tree, right? Object. And what is the first method I should type? Init, right? Because we want it to automatically take those. So underscore underscore init underscore, and what should come next? By the way, is it font big enough? Do you want me to increase it? Yes? Even you say that. Okay. Is it better now? Okay. All right, so what is the first argument here? Self. And second doesn't really matter, but we can say data, right? And so left and right. So let's assume we want left and right to be none by default. Okay. And it also says create attributes for these arguments. So I'm going to say self.data equals data, self.left equals left, self.right equals right. Okay, so this should work, right? Any objections? Okay, so let's test this. T equals 3, let's say 3, and print T dot data. Okay, so it works. All right, so now it says override print so that it prints the value of data. And what's the method we use in this case to override print? Right. So I just copied everything from what we wrote. So, okay, so anybody helps me? Okay, you know too much. Anyone else? Anyone else? Huh? Okay. All right. What else? Okay. And now return self, or right, so you should convert it to string first, right? That data. Okay, this should work. And let's now test this again. Let's create a tree that's called T. And when I say print T, it should print 3. Okay, it works. So everybody is on the same page? Okay. All right, so now create instances left and right of class 3 and assign values 2 and 3 respectively. Okay, this is easy. So left is going to be one instance, which is, I'll take it later, which is created by using this class. And the value is what? 2. And another one is right. It's going to be 3 of 3, right? And let's also just make sure left is let's do this. See if it works. Just testing. right? Just to make sure. Okay, so left is 2, right is 3. Okay. All right. And now create an instance tree and link to the children left and right. Okay, so can you guys type this or help me with this? So instance name is 3. I know it. I didn't say what. Okay, so let's say the data is 1. Okay. 3. Let's say with data 1. Okay, so can you help me? 3, okay. That's a good start. 1. Left, right, exactly. Okay. Okay, so now we are gonna do something more interesting. Write a function, total, that sums up all the data values in the tree. Okay, I'm gonna give you some time to think for this, but so it should be like this, total, and it should take your tree. So you should think about this. How to do this? You understand the question, right?
Yeah. Set a number first. We create a number first, 0, like a total equal to 0.
Okay, you want this. Well, I don't think it's a good thing to give the same name to.
We can change the name.
Okay. I think sum is also used by Python for other things.
Without.
Huh? Without what?
Result, like
A result, okay. Okay.
While left. Tree dot left.
Okay.
Tree equals tree dot left. Result plus equal to tree dot data.
Okay. Okay, while you are thinking on this, what about recursion? So does recursion make sense here? Okay, so let's start with the simplest case. So I'm gonna just comment this out for now, okay? Don't get offended. Okay, so if 3 is none, what should I return? Okay, so I have the base condition. Okay, and so yes, so return 3.data should definitely be there, right? Exactly. And okay, more for the right too, right? Okay, so that's it. Okay. Okay, so let's test this with the tree we just created. Print total 3. Say 6. Is that true? So basically our root is 1, our left is 2, right is 3, so the sum is 6. So it works now. But let's do something a little bit more complicated. Let's make a 3. So 3 of, let's say, the root is still 1, but left is another 3. Let's say that's also root 1, but its left is 2. Actually, no, so what about the 3 we just created? Let's make it like the left side of this 3. And for the right, let's make it 3. Just have one node. So can you visualize this? No? Yes, right? So 1 is the root, and the left is the 3 that we created here, which is another 1, and it also has children of 2 and 3. So 1, 1, 2, 3, and on the right we have just 3, right? So basically we have 1, 1, 2, 3, and this is 3, right? That's what we have. Okay, so the sum should be 6, 9, 10, right? Okay, so let's check our function works. Okay, it works. Was this clear? So again, we just use the recursion trick to compute, to actually traverse through the tree. Okay, any questions here? And remember to have a base condition for your recursion every time. You guys look confused. Okay, so let's go through this tree, right? So is 3 none? No. Then we go to this statement, right? So 3.data is 1, right? And then 1 plus, I compute total 3.left. I'm here, and I say plus 1 again. And then from here, I go to 3 left again, plus 2. And once I'm done, I go to 3.right. And then I go back all the way where I was left off, and then I compute 3. I add 3 to my total. Okay? Yeah, so if you want to understand even more, you can play by yourself, just like adding print statements, how it actually traverses when you run this total function. Okay? All right. So write a function print 3 that takes the 3 as an argument and prints the contents of the root, then prints the entire left subtree, and then print the entire subtree. So this is actually called pre-order. Okay. So let's say let's call this print print 3 that takes the 3, right? Okay, so I want to compute root first, and then left, and then right. So entire left, and then entire right. So any ideas? Yes, again, recursion. Well, let's set the base condition first. If it is none, you don't want to print anything. Okay, so if 3 is none, you can just say return, nothing. And now we can start the print statements. Any ideas? Well, let's first print the data, right? And then I want to finish the left subtree first. Yes, true, print 3. And then I want to go to the right. Okay. Any other ideas? Any objections here? Okay, so I want to test it first with this 3 we just created, and now we can test it with the other expression. So let's call this print 3. Although, I mean, it's unfortunate that we have double numbers of 3 and 1, but let's see. Okay, so what do you think it should print from this? 1, 2, 3, 1, 1, 1, 1, 2, 3, 3, right? Exactly.
It should be T.
Oh, thanks, yes. Okay, and we can actually make it horizontal by just changing this and to this. Okay. Okay, any questions here? All right, so here is another test. I made these pictures way big, but so we have this 3. So data in the root is just plus, that's a string, and the left is 1, and right is star, and from star we have left 2, right 3, and then they all, of course, point to none. So for this, let's create the 3 argument for this. Okay, so I know maybe I should write it here too. So we have none of these. Let's see. Okay, so we have plus, and then 1, and then star, and from star we have 2 and 3. Right, and if I don't have anything, that means they are none. Okay, so now let's create this 3. Ooh, went way too far. Okay, so anybody help me to create this 3? Mm-hmm. So let's call this left so it's more clear. Yes, so we're on the left. Mm-hmm. And right. Two. Okay, so let's put this. And right is 3. Okay. So this should work, right? Let me see. +1 star 2 3. Okay. All right. And now let's test our print 3. Okay, so what do you think it should print? Say it again from the beginning. +1. Okay, so +1, 2, or star?
Star.
Are you sure?
It's a pre-order.
Right, so data, print left, finish left,
Yeah.
and then go right. For right, print data, finish left, and then go right. Okay, so star should come first. So it is +1 star 2 3. Okay, let's see if we are collectively right. Right. Is this clear to everyone? All right. So now let's change the order. This time, print 3 post order. So it prints the subtrees first and then the root node. So you should just change the location of print, right? And you can assume left goes first. Yeah. Okay. So tell me. Is none. Okay. Right. Let's do left first. Oh, okay. Now you tell me. What's next?
Again, right.
Right. And or we can just say 3 too. Okay. So let's run this code for this tree that we just created. So for this, what do you think the result should be? 1, 2, 3, star, plus. So everybody agrees with this. So if you look at the code, we actually finish left first and then right, and finally we go to the root. So first left, and then we skip the root, so we go all the way right. So from right we go to left, and then go all the way to the right before going to the root. So we finish this, and then we go back to star and go back to the the original root. So let's see if we are correct. I again forget this and 1, 2, 3 star plus. Okay. And next traversal is print tree in order. So that takes the tree as an argument and prints the left subtree first, then the root node, then the right tree. So we go like this. So this is called in order traversal. Okay, tell me. Same thing, just change the order. Yes. Is none, return. And now left subtree first, then the root, then the right subtree. What is it? Justin, what do you think? Print tree in order. Okay, and this should be okay. Let's not forget this. Yeah. And just do the right tree too, right? Okay. So if we use again if we traverse our tree using in order, what should we have? 1 plus 2 star 3, exactly. 1 plus 2 star 3, yes. All right, so these are all about the trees and also traversal and also using recursion. Do you have any questions about this? Your next assignment will be about trees for sure. And this is a very, very common problem in interviews too, you know. So these are the easiest questions you will get in software engineering interviews for the tree traversal. Okay, but you should know these basics really well. And also be able to implement them in Python too, of course. Okay, so shall we move to the next topic? Okay, so I wanted to talk about NumPy because I think NumPy is one of the reasons that made Python really popular. So how many of you use MATLAB? Yeah, so you can actually do most of the MATLAB operations in Python thanks to NumPy. So NumPy actually lets us use all those matrix operations and everything you can do with MATLAB pretty easily. So before NumPy, scientific computing was harder with Python. Sorry, before NumPy, yes. Okay, so what does it provide? So that's an extension package to Python for multi-dimensional arrays. So you need to install it. It doesn't come like built-in in Python. So you need to say pip install. So if you start actually running these things that I'm going to run today, you might get an error if it is not installed in your environment. Maybe this might be a good time to say pip install NumPy for whatever environment you are working on now. Okay. Okay, so we also know it's efficient and it's also designed for scientific computation, so it brings some convenience. And it's also known as array-oriented computing. So you think in terms of arrays most of the time. And so the recommended convention to import NumPy is usually you just say import. Anybody knows this? Okay, you guys know it. Maybe we should just skip the class tonight. Just go. Okay, so this is like the convention to import NumPy. So we are going to create arrays, but what can they be like? So you will be probably using some data or some images, whatever, when you use Python. So these might be the values of some simulations at discrete time steps, or they can be signals recorded by a measurement device, or pixels of image, or maybe even 3D data measured at XYZ positions like MRI images. And why is it useful? Because it's memory efficient container that provides fast numerical operations. Okay, so let's just start a really basic array here. Actually, it should have been here. So let's say A is, so anybody knows how to create an array of 1, 2, 3, 4 using NumPy? NP array, okay. All right, and now let's print it. Okay, so now Python knows that this is a NumPy array, what you created. So by using a list, you created a NumPy array to actually tell your machine that you are going to be doing some array kind of operations using NumPy ecosystem. Okay, so now let's see how efficient they are. So we can actually do similar things with using just list operations too. So let's do something like let's take a square of some list, some items in a list. So let's call this is range, create some values, and then so you can actually, so this is a trick to use time. We discussed about benchmarking, but when you are using IPython notebook or IPython, you can actually just use this notation, percentage time it, and here you can write the expression. So let's say we just take the square for all the values in L. So we just benchmarked it. So this is like per loop, this is how much it takes using these list operations. So now let's try to do the same operation using NumPy. So now let's create an array of, okay, so I want to create an array where the values go from 0 up to 1000. 1000 is excluded. Anybody knows how to do this in NumPy? You don't want to type all the values, right? Arrange, have you ever heard of arrange? NP arrange. It's almost like range, but we say arrange, you know. So let's create an array of this, and then let's time it. So now I want to do the same operation. I just want to take the square, and let's time this one. Okay. So one of them is microsecond, other one is actually nanosecond in my machine. So which one is more efficient? First or second? This is nano, this is micro. Nano is more efficient, right? So that actually shows that when you want to do some basic operations, NumPy might be more memory efficient. Okay, so we just showed that. Okay, you can of course read more about NumPy. So they have this documentation in SciPy's webpage, or you can do in interactive settings, np.arrays or whatever function you are looking for, question mark. Or you can also do something like np look for, which actually I've never heard of this until today's class. So I realized it when I was preparing it, but something good to know. So this is how you can get more documentation about NumPy. Okay, so now let's create some arrays. Let's play with those again. So let's create an array of from the list 1 4 0 1 2 3, and let's print it just to see what Python sees it. And then to get the dimension, so what is the dimension of this array? Or number of dimension? 1, right? So this is 1D. Do you know how to do that? Dimension of array A is. Do you know how to do it? No, that gives the shape. Right, exactly. Okay. And so what is the shape? Shape of the array A is, you mentioned shape, right? How do you use it? A dot shape. That's it? Okay. So here, sometimes this may look like 4 by 1, sometimes 4. If you want to make sure it looks like 4 by 1, you just add another dimension. But don't worry about it for now. So this actually shows that this is actually like a one-dimensional array of size 4, of length 4. Okay, so now so we just created a 1D array. So let's create a 2 by 3 array. So let's call it B. So I want to create this one. Basically this matrix 0, 1, 2, 3, 4, 5. Anybody tells me how to do that? Let's type array here. Any ideas? Okay, so it's actually very simple. So you create a list of lists, where the first list is gonna be the row, so 0, 1, 2, and the second list is gonna be the second row, so you can say 3, 4, 5. So we just created a 2 by 3 matrix. Okay, and of course you can say print B. So this is how it looks like. And so what is the dimension of this? Three? 2, right? Yes. Okay, and the shape is gonna be, I think we mentioned it already. So it actually returns a tuple in this case. Okay, so this is how NumPy works with multi-dimensional arrays or matrices. So let's now create an array of 2 by 2 by 1. Let's call this C. And let's say so basically I should create a list of lists, right? So for 2D it was a list of lists, and now it's supposed to be list of lists. So now let's create, it's going to be one list here, another list, and another list. So let's call this like 1, 2. So this will be the end of the first list. And let's create another one, call that 3, 4. So print C. So we can make it maybe more complicated. Let's say, let's make it like 5, 6, 7, 8. Okay, so what is the dimension of C going to be? Right. Okay, and shape? For example, so if I just type C0, it is this. C0, 0, it is that. 0, 0, 0, 1, right? Or what else should we say? So basically we just show that it is 3D by accessing like 0, 0, 0. Now, so let's try to get the shape. So shape is actually 2, 2, 2. So you can either have like C0 as this, C1 as this. So this was 2. Maybe if I make it actually, if I get rid of this, or yes, so let's delete this back. Now it is 2, 2, 1. So if you look at C0, it is 1, 2. C1 is 3, 4. And C1, 1 is 4. But after this, I cannot do 1. I get an error, so it has to be 0. You see, so the last dimension has 1D. And these can be 0 or 1, so it is like 2D. this can be 0 or 1 too, so it is like 2D too. So that's why it's 2, 2, 1. Okay? So here the last dimension you see here is actually this one. So how much you can go here? You cannot go more than 0, so it's only one dimensional. Here you can go 0, 1, so it is two dimensional. Here you can go 0, 1, it's two dimensional. Okay? Okay, so let's move to the functions for creating arrays, although we already mentioned some of those. But again, just to put it to our muscle memory, let's say a range 10. So this is almost like range again. It's gonna create values from 0 to 9, and we can still say print A. Okay, so now, well, if you look at the help of NP arrange, you might actually see more than this. So it actually has start, stop, and step. So basically, we can create an array that goes from 1 to 9 with step 2. So basically, we just want to get the even values. Let's say, oops, sorry. Why does it? So B equals NP arrange 0 to, no, we say 1 to, oh, what's this? So 1 to 9, and step is 2. Say print. So it creates values from 1 to 9 with step of 2, but AND is exclusive, so 9 is not included basically. Okay? Or you can actually create an array using linspace by giving the number of points you want. So let's call this array C. So we want the values between 0 and 1, and 6 of those evenly spaced. So we can say linspace 0, 1, and I want 6 of those. Okay. And let's say print C. But in this case, it actually included the last value here. So it just gave us even spaced numbers between 0 and 1. And since we asked for 6, it gave us 6 values. Okay. So now, what does it say? So create an array between 0 and 1 with 5 evenly spaced points, not including the AND. So, okay, so first let's see what linspace does. Maybe there is some function that some argument that we might be missing. Okay, AND point true. So this AND point true, you can read the documentation here, but that basically means that should we include the AND point or not? So now we don't want to include AND point, so we can say NP linspace. Again, 0 to 1, I want 5 of those, but for AND point, I say false. So don't give me the value of 1. and you can say print D. So see, now 1 is excluded. And of course, there are some common arrays that you will use in scientific computing or linear algebra all the time. So one of them is creating matrices of all 1. All the values are 1. So do you remember how to do that in NumPy? Just want to create all 1s. Okay, so NP 1s. And here, okay, so let's first see how NP 1s work. Okay, you give the shape. You can give the D type that we will talk later. So see, when you say np.ones 5, it gives you 5, an array of 5 values, which are all 1. Or you can actually give the shape either like 5 or 5 comma. Or if you want it to be 2 by 1. So, okay, so we got the idea here. So now it's asking us, it should have the size of 3 by 3. So you just give shape as 3 by 3. And what should we call this? Okay, very interesting name, A. And so let's see what we just created. Okay, so if you want to create such a matrix of all 1s with the shape you want, you can just use this. Okay, so for zeros, any idea? Like your intuition? If 1s is 1s, what is 0?
Zeros.
Very good. Okay, so let's call it B and P zeros and 2 by 2. And we can print B. So we just created a matrix of all zeros. And also you can create an identity matrix of size 3. So do you know identity matrix? Everybody knows identity matrix. What identity matrix is, right? Is there anyone who doesn't know? You don't know? So identity matrix is basically just a matrix where all the diagonals are 1. You can have as many as you want, and the rest is all 0. This is called identity matrix, basically. So you can generate it. So since this is a very commonly used matrix, NumPy has a function for that too. So let's call, so it is I, basically, identity. And you can just say 3. And if we print, it actually prints you this identity matrix. Okay, so you might also think that a diagonal matrix which has the values in the diagonals that you are interested in. So let's say you want to have a matrix like 1, 2, 3, 4, and all the rest are 0. You can easily create that too in NumPy. So there is a function called diagonal, and so you can either, so let's use the arrange that we have been working on. Actually, I want to use array. 1, 2, 3, 4. So if it's, oh, what happened? Okay. Print D. So see, it just created us a diagonal matrix which has the values we want. So here we just gave the values we wanted as an input, and it made it a diagonal matrix, basically. Okay, so random numbers, you might guess that they're also very useful, and we actually already did some exercises using random numbers. So NumPy also has this random module where you can create random numbers. So let's call this a, so np.random. So if you want to sample from a uniform distribution, you can use this rand. And okay, so let's see what does this rand do. What are the default values? Okay, so uniform distribution over 0 and 1. Okay, so do you understand what uniform distribution means? So basically we just want to sample uniformly from the values between 0 and 1 by the number of items we want. So let's say 4 in this case. So in this case, with this statement, it actually gives us values, like 4 values which are completely random or randomly sampled from this distribution. But you might guess that what if I don't want uniform distribution? What if you want to sample from a Gaussian distribution? So for that, okay, let's call this B. np random dot rand n, and let's create 4 again, and print what it has. Okay, so but you realize we have some negative values now, but we didn't have any negative values when we did it from the uniform. Do you know why, or do you have an intuition why we are getting negative values here? Okay, so let's look at the explanation or documentation of this rand n, how it generates. Standard normal distribution. Okay, what's a standard normal distribution? Oh, that's a distribution of mean 0 and variance 1. Okay, so this is actually sampling from the values where the mean is 0. If the mean is 0, of course you are going to have some positive and negative values. So when you sample, it's normal to have some negative values, right? But for the uniform distribution, you were sampling from between 0 and 1, which are all positive. That's why we didn't see any negative numbers. Okay, and if you want to get the same randomization every time you run it, if you remember, we had this seed idea before with the random module we discussed. So here you can actually say np random seed, right? Yes. So you can give your zip code. I made it up. Okay, so then you will always get the same numbers. So let's say oh, but okay, sorry, no, we can't. Okay, sorry. So we actually need to. So every time when I restart IPython notebook, run this, I'll get the same values. Okay, but I don't want to do it now. But it is actually to tell that if I'm running something in some experiments in my machine and you are running something in your machine, I want to make sure that you are generating exactly the same values as I'm doing. So it is good for consistency to have this seed information set to some value. Okay. Okay, so let's talk about the data types. And just an array of 1, 2, 3, 4. And so let's print type of A is. So do you know how to get the type value of a NumPy array? Okay, so it is actually a D type. So what do you think the type of this array might be that we just created? Array? Say array. This is actually, so this information, okay, let's see what it says about this D type. Okay, NumPy array is homogeneous, contains elements described by a D-type object. So that's actually the type of the elements. Okay, so for example, okay, we'll go through them anyway. But so in this case, so we have these elements of the array. Then when I look for the type, what do you think it should be? Integer, right? What if I want to make it float? If I put this and run this again. So what do you think it's going to be now? Float, right? Okay. Okay, so yeah, so in these examples, NumPy just automatically detects the data type from the input, whatever actually you give. So these different data types also allow us to store data more compactly in the memory. So if you don't necessarily need to use floats, you can just use integers to save some memory. Or you can also specify the data type you want. Okay, so if you look at so before we do this, if you look at how you create an array, there was also a D-type information that we never entered so far. So you can actually mention the type you want. So let's call this C, P array. Again, 1, 2, 3, 4, and D type float. And if I print, what was my notation? Okay, type of C is okay, so it knows it's float. We just entered it. Okay, so there must be a default type too, right? So let's create an array of ones again. Call that A, P dot ones, have 3 by 3 and type, print the type again. Type. Okay, so it is it generates float by default. Actually, you should have noticed it from how these ones look like. You see it, so this array, they all has these little dots next to the numbers. That actually indicates that it's a float anyway. And of course, there are some also other types, like for example, one is complex type. So let's call this D array. I don't know, 1 plus 2j. Actually, so Python knows that this j is the imaginary number. And 3 plus 4j, 5 plus 6j. And let's say print type of D is D type. So it knows that it's complex. And this 128 because it has two values, 64 bit each. That's why it's 64 times 2. Okay, so you can also create an array which is which consists of Boolean values, true or false. So in that case, let's call this p dot array. No, we can say true, false, false, true. And again, we can print the type. Okay, so it knows it's a Boolean. The elements are all Boolean. What about strings? So let's say f numpy array. Let's say bonjour, hello, hello. Okay, so here now let's look at the type of this array f. Type of f is f dot d type. Okay, so actually this indicates that it's a string with maximum of 7 letters, so it knows how much to save. It's good, it's efficient for the memory. Okay, so now we should feel pretty comfortable with creating arrays and also the most basic matrices that we are interested in. So let's do a little bit of visualization. So how many of you used matplotlib in Python? Matplotlib? You? Okay. Alright, so this might be a little boring for you, but so if you want to use this plotting library, matplotlib, in IPython notebook, let's say, so I always look this up. So it's like percentage matplotlib inline. This is just to tell your notebook to actually keep the figures you just created in your notebook, basically. And so this is also another convention to import the plot functions that you usually use. So you say import matplotlib.pylab. I always look this up to pyplot as PLT. Okay. So instead of every time calling matplotlib.pyplot.plot, you just so this is like a convention, and you just call PLT, the plot, for most of the things you will use. Okay, so now let's create array, call this X, where the values are between 0 and 3, and it says 20 points. So do you remember what function we will use for this? Huh? Just 20 minutes ago. Okay, linspace. Okay. So I can say 0, 3, 20. And now let's create Y. Linspace. So this one is between 0 and 9, but again 20. So make sure they both have 20 points, because I'm going to plot them. If they don't have the same number of points, I'll have some trouble with the plot. Okay, so now we can just say, let's say you want to plot X versus Y. So X in the X-axis, Y in the Y-axis. Just say this. So it just creates the plot for you. Okay. But of course you can do it differently. If you just want to do, so this was a line plot. So what if you want to do some dot plot? Y. Let's say this. Okay. Yes, or I can do X too, or star, or I don't know if this works. Oh, sorry, didn't work. Okay, this worked. Okay, so there are several options with the plots. Let's go back to this. Alright, so this might be useful, especially if you are interested in data science, machine learning, some data analysis, whatever. So you'll be using this all the time, because it's important to understand your data, how it looks like. Okay, so now let's plot images. So for that, let's create just a 2D array from just like random numbers. So let's call this image numpy random. Let's create from uniform values and 30 by 30. So I created my image. You can actually take a look how it looks by just print, but it's really hard to see, right? So you don't want this. But these are the values it looks like. So it's better to plot this. So when you plot, you can actually use this, instead of saying plot, you can say imshow for images specifically. And you can also give the color map you want to use. So in this case, I'm gonna use color map hot. And also you can add the color bar. So this is how the data you just generated looks like. Of course, it's random values, but this was just to show you how you can use this imshow function to plot 2D images. All right. Okay, so let's move on. Again, I'm gonna create my famous A array and P arrange up to 10. I know how it looks like. So let's say I want to access the values at indices. So ninth index is actually the last one. So if you want to access the indices of like 0 or 2, or you can actually say for 9 you can just say -1, right? Because it's the last one, last index. So it gives, so this is how you do indexing. You know, so this is like a usual Python, what we will do with lists or strings anyway. So when you say -1, it knows that it's the last element. And for to reverse an array, this is, I don't know if you will ever use this, but this is like, so how you reverse an array. Yeah. Okay, so create an array where diagonals are 0, 1, 2. So let's call this A and P. So like what we did before, diagonal. And we can say NP arrange 3. So we are going to start indexing or slicing from this. But first, let's see how it looks like. So this is the matrix I have. So if you want to access the indices of, let's say, 1, 2, you can just say 1, 2, or is just 2, yeah, 1, 2. So this is like 1, 2. So this is 0. It's giving to you. Okay. So the row 1 is actually the second row. Column 2 is the last column. So it is this value that returns. Change value at indices to 1 to 10. So that's actually third line, second column. So let's see, 2, 1. We can assign a different value. And then if we print the array, we will see the changes. So we just made this value 10. So it is the third line and second column when we say 2, 1. And so if you want to print the second row of the array, what do you do? Wow, yes. Okay. So very similar to the standard list, but it has some memory advantages, especially if you are doing some computation. Okay, so now slicing. So again, let's create this array. Range 10, and we know how it looks like. Okay, so slice from 2nd to 9th index with step 3. Any ideas? So assume that 9 is included. This is actually this is how it looks, how it should look like. Start, end, and step. So basically 2, 9, 3. So it gives us 2, 5, 8 with step of 3 every time. Slice from 1st to 3rd. So basically you can just do this. So it gives you this slice when you do 1 to 3. Okay. Slice all with increment 2. Any ideas for this? We want everything, but increment 2. So this is how you do slicing, start and step. But let's say we want all. When we want all, what do we do? Okay, so this is how it should look like. So if you want, so from start to end, you just want to have everything, and the last one is actually the increment 2. So now we just have all these even numbers from our original array. So we got 0, 2, 2, 4, 6, 8 when we did that. And slice from third to end. Any ideas? 3. Yeah. Well, you don't. So you just need one column. Yeah. Okay. So let's look at this illustration of all operations we did here. Where I should make it smaller. Okay. So the first one, it says 0 on the row, and for columns go from 3 all the way to 5. 5 is not included. So 0th column, so this is my array, let's say, and I want 3 all the way to 5, but 5 not included. So this orange is the slice I'm getting when I run this. Okay? You look confused.
Is the 3 is index or?
It's the index.
The third is 2.
0, 1, 2, 3. 0, 1, 2, 3.
Yeah, so 3 is the fourth, not the third, right?
3 is what?
The number 3 is the fourth number, not the third.
No, but index is 3.
Yeah,
Index
but
of 3 is also 3.
You command before you say third. Can you go?
Okay.
Yeah, you say slide from the third to end. So
Okay. All right. So it was actually more.
index 3 actually.
Yes. So I should say from index 3. Okay. But this is just a comment. So here, what I really meant is, so 3 is actually the index for the fourth item, right? Because they start from 0. We all know it, right? And it goes all the way to the 5th index. But 5th index is not included. So it should have only 3 and 4. Okay? And, okay, so let's look for this one. So from row index 4 all the way to the end. So 0, 1, 2, 3, 4. Okay, so I'm gonna start from here all the way. I'm gonna go all the way down. And for the column, it's again from 4 to all the way to the end. So this is like 0, 1, 2, 3, 4, from 4 to all the way here. So you are looking for an intersection here when we run this. So all the values that start at row 4 and end at the last row, and all the values that start at column 4 and end at the last column. That gives us this box here. Okay, what's confusing here, you think? So if I told this 4 to 6, so let's say this was 4 to 6, 4 to 6. That could have been more intuitive, right? I said 4 to 6, 4 to 6, so just look at. So here, instead of typing 6, you just say all the way to the end. I know it has 6 rows and 6 columns. So this way, we actually look for the intersection, all the values between row 4 and 6 and column 4 and 6, which is this little region. Any questions? Okay, so maybe we should look at others, then we'll come back to this one. So this one is all the rows. So this means all the rows, and this means column index 2. So column index 0, 1, and 2. And we want all the rows here. So it's going to be all these red region. Okay, that one was easy. So what about this one? 2 column 2. So start with the second row, whatever, so this row. Increment by 2, look at this row. And also make sure you have all the columns, all the start to end, but with increment 2. So start to end, increment by 2. So all these columns. So the intersection is this green region. Okay, so let's go back. So 2 column 2. It gives us, so we all agree that it gives us this row and also this row, right? We all agree, right? Okay, so if we didn't have any constraint for the columns, we could have gotten these 2 rows only. So we will have only these 2. But since we have this, oh, what happened? Is it touch? Oh. Okay, I guess it was this. Okay, I shouldn't have too much. Okay, so if we didn't have this, it was going to be this row and this row. But since I have this constraint, I have this column increment by 2, this column increment by 2, this column, and the intersection is those green regions. Okay? And then if you go back to this one, it is again, so if we didn't have the constraint for the column, if we only had the rows, we were going to be only rows 4 and 5. But we are also saying that, well, we only want the columns 4 and 5 too. So this is the intersection. Okay? Yeah, you need to be really careful when you implement things with NumPy. If you are doing some slicing operations, you need to be careful which, if you are getting the slice that you are looking for. Okay. Okay, why do I have this so many times? Okay, so now let's, so we have this array A again, right? Which has all the values up to 9. And assign the values after index 5, I should say, to 10. So I'm gonna, okay, so how do you get, this is too small, right? How do I get all the indices, all the values, including index 5. I mean, after index 5, that includes index 5. 5. Right. And then I want to assign 10 to those values. And then if I print the array, see, all those values became 10 now. Okay, so now let's create an array B. So 0 to 4, 4 included, so I should say 5, let's say. Okay, so assign reversed B to all values after 5 of A. This is actually a good quiz question. Any ideas? So this part I know. Right. So I want to assign B to the last values of A. If it was just B, we would be like this, right? We could just say B. What if you want to reverse it? Increment -1. So now print A. So see, so all these values were 10. Now they became 4, 3, 2, 1 because B was 0, 1, 2, 3, 4. So since we just reversed it, we actually assigned the reversed values of B to the original A. Okay? Okay, so remember we talked about the lists when they are immutable, or there are cases where when we create a copy that's actually independent of the original list, but if we don't do it properly, we might just refer to the same value. So when we change one list, that might affect another list that we originally created from if we don't copy it properly. You remember that? So same thing applies to NumPy arrays too. So when you do a slicing operation, that actually creates a view on the original array. So it doesn't create a copy of it. So it's just a way of accessing array data. That's it. So the original array is actually not copied. We are not creating a copy when we use these slicing operations. And one way to check that is actually you can just say may share memory. It's a little bit interesting name because it's not as consistent as you expect it to be or you want it to be. So you can use this function to check actually if they are copy of each other or not. So now let's test this. I have this array, and I'm going to create B that takes only the even indices from A. What do you do? Just give me the even indices. Yes. And let's print A. Oh, sorry, print B. Okay, so these are the even indices, right? Okay, so now let's see if they actually share the memory. A and B. Do you think this is going to be true or false? True. Based on what we just said. So in this case, let's modify the array B by just assigning 12 to it. And we can print B again. Okay, so we just changed the first value to 12. And now let's say print A. See, A also has changed. So again, to summarize, we created this array, A, and then we created another array, B, using the original array, A, that only takes the even indices. And we show that they actually share the memory, which indicates that B is not a copy of A. So we didn't create extra memory for B, actually. And then when we changed B, some of the elements in B to something else, we realized A also has changed. So this is something we need to be careful, right? You may not intend to make a change in A. Or sometimes it could be intentional too, but it's good to know what's going on. So now let's go back to the original array. Okay, so now I'm going to create B as evenly spaced items. I think that's it. Yes. So here we are actually force a copy. Or let's call this C. Okay. So first print C. Okay, so it has the same values as B, or B that we originally created. And now let's change the first value of C to 10. And of course, C is going to change. So now my C is this. And now let's look at A. A didn't change. Why? Because of this, we can say may share memory AC. This is false because we created a copy in the memory for C using A. Okay, so is this clear? So basically, if you want to make independent operations, so this is the way you should do. You just create a copy of view. But if you actually don't want to create extra space in memory, you can just use it this way, just slicing. So that will be more memory efficient. But you'll be changing the original array when you modify the view. Okay, fancy indexing. So NumPy arrays can be indexed with slices, but they also accept Boolean or integer arrays. So for integer arrays, we call them masks. So this method is called fancy indexing, and it also it actually creates copies, not views, which is so it's good to know. Set C to 3. Why do I need a 3? Oh, okay. So I'm gonna create some random values. So for that, in order to make sure you guys also get same values as mine, I'm gonna set it to 3. So now let's create an array that contains 15 random integers from 0 to 21. So one way to do this is actually you can use NumPy's random modules randint function, and you give the start value, end value, and number of elements you want. And we can just print this. So these are the randomly generated values. So you should get the same values too in your machines. Did you get the same? Good. So this seed thing is working actually. Good, we just confirm. Okay, so now let's check if items of A are divisible by 3. Any ideas? Or just return false or true for each index.
Do like the modulus with the length of
Modulus with what?
the length of A.
I think it's simpler than that, since these are
Oh,
arrays.
you can just do it.
You see?
Oh, for each. Okay, I thought you meant the entire, like the number.
No, so I want to know which items here can be divided by 3.
Yeah.
So this is true. This must be true. Did I miss anything here? Oh, so this is true too, of course. Okay, so now let's create a mask for this. Let's call it a mask. And just assign what we had here. 3, 0. Okay. And create an array extract from A that's created from using the mask. Okay, so let's call this extract from A and a mask. That's right. Or you can also do this too. Okay, so now let's print this. Okay, good. So all these values have modulus of have value of 0 when you take the modulus of 3. Okay, so now let's check if they share the memory. A and extract. Okay, so they don't share the memory, which means by using this mask, we actually created a copy of the original array. So modifying extract from A doesn't imply modifying A. So for example, let's say assign -1 to the items divisible by 3. Do I want it? Okay, I can use the original one and mask assign -1. See, so all those values now became -1. But if you look at the, if you look at the extracts from A, so it stayed the same. All right, so indexing with an array of integers. So apart from mask, you can actually just give the array of integers to your array and then get the indices you want, or do the slicing you want. So for this, let's first create an array, arrange 0 to 100, and I want 10 of them. I mean, with increment 10. So A looks like this. So get indices 2, 3, 2, 4, 2. So basically all you need to do is you can take all this. A, this, Okay, so here what I did is get me elements index 2, index 3, index 2 again, index 4, index 2 again. So you can just give these values. And we can also assign values like, for example, all the values in this list, which are 9 and 7, assign -100 to this. So if we print A, we see that we just change the value at those indices to -100. Okay. So this is all about slicing and indexing. Okay, so element-wise operations. So in NumPy, it's pretty easy, straightforward to actually do these kinds of operations. So I can just say a plus 1 and it works. So basically to each element I'm adding 1. Or you can also compute 2 to the power of your array. So it computes the power of 2 to the power of each of these elements here. Okay, so it's also convenient. So all arithmetic operations are element-wise. Create an array B from 1s with size 1 and add 1. So let's say B and P 1s 4. So now we have array B, which has all the values 1, and we have array A, which is this. So we can actually just run A minus B. Wait, is that correct? So we just subtract 1 from each of those. Subtract 1, so it will be 0, 1, 2, 3. 0, 1, 2, 3. Or if you do multiply, it actually doesn't do matrix multiplication. It multiplies all the elements so it does the multiplication element-wise. Okay, so first element of A is multiplied by the first element of B, and second element of A is multiplied by the second element of B, and so on. You know, I think this part is pretty usual. Okay, so also now, yeah, these operations are of course much faster than if you do them with pure Python. So let's do this again. So let's say A is and P arrange. Let's say it has 10,000 values. All right. And then I'm going to use this time it A plus 1. Okay, so now let's do same operation without using NumPy again. So is range 10,000 and time it I plus 1 for I in F. See, so this is much faster. This operation is much faster when you do it with NumPy compared to the usual way using lists. Okay, so this is important. Array multiplication is not matrix multiplication again. So let's create an array of ones. Size 3 by 3. Okay, so what do you think it should look like? If I do matrix multiplication, what do you think it will look like? The values? No, matrix multiplication. So let's say I'm gonna do matrix multiplication of C with itself. C matrix multiplied C. Do you remember matrix multiplication? Yes, another matrix for sure. Yes. What are the values of that matrix? 3, right? So all values should be 3 if you multiply it by itself. Okay, so let's see if this usual multiplication will give us that. No. So this actually did element-wise multiplication with all the values. But what if you want to do matrix multiplication? You can actually do use these dots. So that gives the correct matrix multiplication value. Okay? So take-home message is multiplication in NumPy is not the matrix multiplication you think, it's an element-wise multiplication, which is an important thing to know. If you are writing some programs that require matrix multiplication or modification, this is important. Okay, so if we look at the comparisons, let's create an array of array 1 of 2, 3, 4, and array of B. 4, 2, 2, 4. So we can actually check the equality for matrix for arrays. So basically, you just say B. So it also gives you the element-wise result. So basically, for each element, it checks if they are equal to each other or not. So here, 1 and 4 are not equal, but 2s are equal. 3, 2 are not equal, but 4s are equal. And you can also do this, A greater than B. So A is only greater than B for this index, which is the only true case. But if you actually want to check if two arrays are equal, so here I just created these arrays, A, B, C. And you can actually, so it actually gives you that they are not equal. But for A and C, since they are the equal ones, just say it just gives true. Okay. But let's also check if they share the memory. A and C. Do you think it's going to be true or false? So A and C have exactly the same values, and when I say array equal, that actually gives me true. But when I say may share memory, what do you think? Why? Yeah, we just created another array, right? Yeah. Okay. Good. You can do logical operations too, like logical OR or logical AND. I'm gonna skip these. So, you know logical OR, right? And this is the logical AND. And also, you can do some transcendental functions, that means analytical functions. So let's say this is my array. You can actually compute sign of A. Oh, sorry. Or you can actually compute log or exponential. You know, so NumPy provides you these tools too. Okay, I guess I'm gonna stop here. So we'll talk about other reductions, summations, and other things next week. And next week I will also introduce pandas. How many of you heard of pandas? I mean the library, not the animal. The library, right? Okay, now less people. Okay, yes, so we will also talk about it. And other week, it depends on the number of people who are doing their projects and also how much progress they made. So we might also get into some machine learning topics for the last course. But yeah, I'm waiting for your progress with the projects. So please send me your updates, okay? All right, thanks everyone.